Hello, Internet. This is JF, and I suck at ATS. There's a guy, Bob Martin, who writes about test-driven development, among other things, I'm sure. And he says that test-driven development is he says it's like a double-entry bookkeeping. So double-entry bookkeeping is an accounting practice where you write the same, like for every transaction you have, you write it down twice in two different ways. And that way later you can say, at the very least, you can go through your books and balance them. You say, okay, these two sets of information, they actually match up. So they're probably legit. So it helps accountants out. And test-driven development is similar in that you encode the behavior of your program in your program, so you can see that when you run it, when you interact with it. And you also encode the behavior of your program in your tests. So your tests run parts of your program and make sure that they do certain things. So at the very least, you can compare them against each other. You can say, okay, do my tests match up with my program? If they do, good. That doesn't mean you don't have any bugs. Just like a transaction might be fraudulent that you put in your books, but it at least means there's agreement there. So if you think about like ways to verify that a program actually does what it's supposed to, well, there's one way. There are basically two ways. One of them is you check the program, just the source itself, and say, okay, is it talking nonsense? Is it just gibberish at any point? Is it saying things that are ridiculous that don't make sense? If that's the case, then there's probably a problem. It says you're saying, okay, the program is like contradicting like the tools used to build the program at that point. So that's what your compiler does. That's what various parts of your build system will do. You run them and say, okay, if make works, if GCC accepts your program, then it's at least not complete gibberish. But then, does it do what it's supposed to do? Well, then at that point, you can't just look at the program. You have to compare it against other things, like a specification, or your unspecified desires, or some other program that you're copying, or something like that. You have to have a comparison. So tests are an easy comparison that you can make. That at least encodes like intentions, or we definitely don't want this to happen, so make a test that tests against that case. So we definitely want this to happen, so make a test that checks that. So that makes a lot of sense. You have your program expressed in two different ways, and you can compare them, and that helps you take care of a lot of cases. Helps you do a lot of verification that's otherwise very, very difficult to do. Like in fact, like the normal case of like somebody sends a bug report and they say, hey, I ran this and it did this thing that I don't want. Okay, well, if you look at the code doesn't say that somebody doesn't want that. The code probably says, okay, it does those exact steps. Like the code has the error written into it. Like it's just a bad design or a bad intention. So you can't really just analyze the code in isolation to see that problem. You have to run it against other people and against the specification and so on. And that, of course, is time consuming and it's active. It's not something you just run a command and have happen. All right. So test makes sense for that reason. But there are two problems with tests. I think one of them, a light problem, is that it's a property of your build system. It's not a property of your language, your compiler. So you have to go out and type make, and your test tools may not have all the information and so on. But the flip side of that is your tests are very free in what they can do. So you can do things that your compiler can't support. Like you can spin up a headless browser and say, okay, render this page, doesn't make sense, and can you see this element, or so on. Or you could ask him. You could literally ask him a mechanical Turk, go have a human look at this. Like, does this color scheme look disgusting to you? Or you could run it against a lot of authoritative tables, say chemistry knowledge, or do these reactions. Are these reactions actually possible? Based on what we know, or you can run against trigonometry tables. Say, okay, run this trig function. Does it match up with what it's supposed to do? That kind of stuff. So the flip side of it not being part of your build system is that at least you can do a lot. You're very free with what your test can do. So that's a minor point. I think the more serious point is that it's actually not the same information. Like with a double entry bookkeeping, it's like the exact same thing expressed in two different ways. With tests, it's not the exact same thing. You have your program, which is 100% of its behavior, and then you have your tests, which are what, like 1% of your behavior. Like even if you have like a test for every function, or if you have thousands of tests, like they're still not going to include. They're not going to encapsulate your entire program. Your program is like, it looks like, say, like a continuous range of behavior, and then you have a bunch of tests. Like this is your coverage. Even if you have a tool that says, 100% coverage, like your tests just don't have that information. But even so, I mean, that's the other thing. So if we were to improve on that, we'd want to have like, it'd be cool if like our duplicate information were part of the language. If we're part of like the actual tools, if we're something that was supported, like you don't get an error if you don't write a test, unless you have your build system do that. Like that would be a test in itself, saying, you've got a function but no test for it. You could do that, but you don't get an error if your tests are poorly written. You don't get an error if your tests are stale. You just unless they go, unless they start failing on you because they're stale. But anyway, it's just your compiler doesn't help you with your tests. But it'd be cool if your compiler could help you with something like this. And this is where we get to ATS. So, because ATS does do something like this, it helps you put the same information in two different ways in your program, and then you can compare them. You can connect those two different ways together and ensure that they actually match up. So let's look at this right here. As a data type, I say jobs. This is a simplification of Final Fantasy jobs. So we don't have red, white, black mage here, just mage and wizard. So fighter, thief, monk, and these are other jobs, but these are actually promotions. So a fighter can promote to a knight, a thief can promote to a ninja in this game. And then you have some functions that deal with jobs. Like a tanky start is a fighter, or if you want to promote, like here's a function that actually works. It goes through, you give it a job, and it'll promote it. It'll pass you that. And if you give it a job that's invalid, with the minus here, it'll throw a runtime error. So if you say promote like a knight, it'll fail the case and then throw a runtime error at that point. And then we have, these are sort of tests because we're, instead of like binding to a variable, we're checking, right? We're comparing it directly with a value. So tanky start here, if it has to return a fighter. If it doesn't, then we'll get a runtime error. And if you promote a fighter, it has to return a knight. If it doesn't, we'll get a runtime error. Now it's all, these are basically tests written in the program. But in this case, we could write a test that runs to make sure it errors out in those cases or something like that. But the point is, we'd rather not have runtime errors. We'd rather have compile time errors. We'd rather have compile time checking. We'd rather have double entry bookkeeping, like having our program expressed multiple ways and with the compiler ensuring that this match up. So how do we do this? First, let's go ahead and make this. So yeah, that works. We're not actually doing anything, but if we had an error, like let's say if I expected tanky start to return a monk, that would not be the case. Yeah, unmatched value at runtime. It's not a monk, it's a fighter. Or if and there are also other cases of error, classes of error, like we could have promotions wrong. Like say a mage actually promoted to a ninja. Yeah, that's not a problem. We'd have to have test coverage to see that happen. All right. So how do we sort of bring this up a level? Bring those runtime errors into compile time errors and start doing a sort of double entry bookkeeping thing. This brings us to a feature of ATS, which is like this is why you would use ATS. Like even if the language didn't have this, it would still be pretty good. But then you'd be like, well, this other language has more investment, there's better documentation, or it has more users. This is why I'm using ATS. This is why you should use ATS. This feature right here. This is actually, this is only the start of it. There's way more. But to begin with, all right. So let's go to this job and say, instead of just being a bare job, we're going to be making a job event. So it's not a parameter. It's just we're refining the type. So the job is now refined based on ints. So all of these now have to have an integer associated with them. So this is not an argument. It's not like fighter is now a struct, then you can carry an int with it. No, it's the fighter is still a constant, and this could be anything, but I'm going to go ahead and just call this 0, 1, 2, 3, And just count them off. Yeah, 0 to 7. So now all these jobs now have a number associated with them. Now this number doesn't exist at runtime. You won't see it in the C source or anything like that, or any generated source. It exists in sort of we're getting double entry bookkeeping. It's a number that exists in like another realm. It's not even called like a type. It's some other term, so I'm not going to get into. All right, but anyway, this point is a fighter is associated with a 0. So if we left it like this, it would actually fail to compile because hold on, is it complaining about 7? No, yeah, it's complaining about like all these jobs. We don't have a job data type anymore. We have a job event. So we have this job event, and so all these other things need to be job ends where I have to reintroduce the old, unrefined job. In fact, you might do that. You might have like a normal job like this, so that people can use interfaces that are refined or unrefined. But anyway, we're just going to go and adapt the program to use ends now. So there are two ways to do this right here. So tanky start, it returns a job, and that job happens to be a fighter. So I could say, let's just create an int. So there's n now is some integer. And job is the job is just in. So there's some kind of job, and the job happens to be a fighter. This gives me the exact same protections as we had before with the old one. I still can't compile it, so then this is converted. But it doesn't actually say anything more than that. It just says job, basically what we had before. But I can go farther than that. I can say, it's actually a job of 0. So it's specifically a fighter. So if I change this to be mage or anything like that, that would be compile time error. And it's a compile time error, not because there's something intrinsically wrong about it being a mage. It's because it no longer matches up. It's like our double entry bookkeeping. I'm stating here that it's a mage, and I'm stating here that it's a mage, and they have to match up. Okay? So, and creating a fighter is the same way. Like I said, it's not a parameter. It's just if I were to add a parameter, I'd be of string int or something like that. No, it's normal constructor. And to promote, similarly, we've got to establish that we're talking about an integer here. And the job would be, let's see, so it can be a value. Actually, great, could go in this. So let's start out by not actually doing anything. So we're just going to say, yeah, this job, and it returns some other job. I can do it like this too, in event. So yeah, it takes a job of some kind and returns another job of some integer, and we're not saying anything about those numbers. We're not saying anything about them in isolation, and we're not creating any kind of relationship between them. So since we're not establishing the relationship, there's no protection here. If I could still have all the errors I was talking about before with this. I'll go to these tests. So this will now, we can actually go to this minus and make that a plus. So that's now a compile time error. And for the night, we still can't make that a plus because this doesn't give us any guarantees. All right, so now it works. And successfully does nothing. If we go over here, make it a plus, it'll say, a really horrible error. Yeah, so the pattern match is no longer exhaustive, and that's a problem now. And also, there are unsolved constraints, which are above. It's only complaining about it being exhaustive now. All right, but we can go make this work by say, okay, so promoting. If we want to promote a job, it's going to be one of these first 4 into one of these other 4, and it's always that. So, and it's not that magically it's not. Oh, it's just part of nature. A knight a knight is 4+ fighter. No, it's because of how we set the numbers up here. A knight just happens to be, because it's written down like this, 4+ fighter. So we can encode that. We can put that into. We can tell promote about this, about the nature of the types it's dealing with. So okay, so now there's an N and an M, and M is n+4 always. So the resulting type is always going to be 4+ the type that comes in. And also, we can just leave it like that, actually. But no, we'll say also, and it has to be, greater than or equal to 0 and has to be less than or equal to 3. So yeah, it has to be fighter through mage, and then the resulting job has to be whatever the input was plus 4. Now I can change this to a plus, just now exhaustive. What did I do there? What did you like about that? Line 9, 25, line 9, 25. Fine. Alright, this is okay. We didn't like that down there. So fighter is plus 4, D is plus 4, monks plus 4, mage plus 4. These are all good. This looks right. I think it doesn't like. All right, let's test this first. There's something wrong with the knight down here, but okay. So fighter, let's say this returns a monk instead. So I've written the promotion wrong. Yeah, that fails the constraint, and specifically it's saying what 2 isn't equal to something. Yeah, errors are still very difficult to read, but anyway, that's not legit. Or if we didn't list one, then it wouldn't be exhaustive. Yeah, pattern match is not exhaustive. It doesn't have a monk. All right, so it has a monk now. We've already showed that you can't do it wrong. You couldn't have a wizard that promoted to a mage. That would be absurd. Not saying, hey, there's supposed to be a mage here and there isn't. Let's suppose we had a mage though. Yeah, there's definitely something wrong with. Let's try doing this. Int. I feel like it's not doing that. Like, this shouldn't be the case. It shouldn't allow the wizard there. Yeah, it shouldn't allow the wizard to promote to a mage because it's no longer like this is a 3 and 7. 7 plus 4 isn't 3, right? Okay. That's what I said. Int. And let's make it a nat and cell. It still accepts that. So I'm saying it's an int. I'm saying the int is less than 4. I'm accepting a job of that type. And it allows wizard to be there. All right, that's unfortunate. That might actually just be a problem with the language, because even though this can never happen, like it's allowing it. But if I had, I'm not sure how I'd test that. But anyway, if I didn't have one of these, it's definitely not complaining that wizard isn't there. Whereas if I had, let's say, less than 8, if I said less than 5, they'll definitely complain like, hey, you should have a knight here. Yeah. So, well, it's mostly right, but it's not catching this particular error. It's not saying that you shouldn't have a knight here for some reason. Anyway, for the most part, just by having these relationships, n has to be, then that first. Yeah, it was actually accepting, like, the line I had before was working, just it didn't cover that case. I thought it would. So I can do it in the same way, saying, I could have the exact line I had before with like N and M all set up and having all the cases in here. That was fine. Okay, but anyway, I'm saying it's getting an N, a job of N, which is less than 4, so it knows that it needs these. And in fact, if I were to pass it like promotion of it would catch that. So saying, hey, I passed it a night, and the night is not less than 4, which that the error actually means there. Okay, so it doesn't find like bogus additional cases. It does find everything else pretty much. Okay, so before I had just promoted, it'd take some kind of job and return some kind of job, but now I've told ATS more about it. So it's not just some kind of job; it's specifically these jobs. It doesn't just return any random job; it returns specifically a one-to-one relationship. A fighter has to return a knight, a monk has to return a master. Going through this function. And this has no effect at runtime level. This isn't done through extra checks. This is all statically, and this is all from static analysis. So ATS just maintains this. And if I ever screw up, like when just now when I tried to add this, that's a compile time error. I won't allow that. It'll tell you, in fact, as best as it can tell you what the actual problem is. All right, let's see if this works now. Yeah, that works now. And if I try to say the fighter would promote to anything else, promote to a mage, that's wrong. Does promote to a wizard, that's wrong. Yeah. So this is all, it's a little bit contrived, This one is as well. So now we have a property, and the property is it's counted. So we're saying that we have integers, and you can have counted integers. And how do you get counted integers? Well, there are 2 ways. You can start with 1, or you can start with a previous count. So this is this over here, and this is the parameters of the prop constructor you'd make. Like down here, like there are no parameters here, but counted in does have parameters. So the parameters are on the right, just like with that type, and it creates a counted next, which is it's refined by the n. So if I give counted, if I create a counted 1, which I'd get from counted start right here. So this is a counted 1. If I gave it a counted 1, then return a counted next 2, or return a counted 2, but I have to create it with counted. The prop is still counted, but the constructor is counted next. So to create a counted 2, I have to say counted next, and then pass it a proof, which would be previous counted. So counted start in that case. So this is all just kind of playing around this property. And properties like this is how you would do something like, not just confirm like simple numerical relationships that you associate with data types, but this is how you would confirm things like, is my factorial function implemented correctly? I have some weird math, or Fibonacci, these are all examples in the case, but you say, are they actually correct? And this is, again, kind of just, I try to think of like the simplest possible property. This one is literally just, can I start at 1 and finally get to a number? If I start at 1 and just add stuff, and just keep saying, okay, counted next of that, can I finally get to the number? So yeah, you can use this and it works. So, these are all creating things. And one thing I point out about this is that just like before, where I said I could say, okay, job in returns job in. I didn't say there was a relationship, and therefore I got no protections. Count and start doesn't, if I pass this along with a random number, it's not going to complain. Like, this actually says nothing about the number that's passed with. I'm passing in a proof constructor as a counted 1, and then random numbers. So that works. Proof count. So yeah. So N1 is 1, 0, 2, just like it's right here. And you'd be like, okay, well, I don't want it to be just random numbers. I want there to be a relationship. well, then you've got to connect them again. You've got to use the system to say that there's a relationship between them. That's what I do down here. I say it's not just a proof and a random number. There's an n, and it's a counted of that n, and the integer is also refined by that n. So if it's a counted 5, it has to be it has to be 5 as well. So in this case, if counted start, if I were to say 5 right here in this case, that's an error. It's got to be 1. It can't be anything but 1. All right. So if a function that does something similar, I say, okay, I take a proof function and I take an integer, but I don't establish a relationship between them. Just two separate, the count of n and the end of m, with no relationship stated. So it says we definitely counted to blah. So in order to call this function, I have to pass it a proof statement, but it doesn't actually do anything. So we definitely counted to -3 and -13. It's like, no, actually we didn't, and that is a lie. We go over here, counted 0, saying, okay, here's an n, it's counted, and there's a counted n and int n, and yeah, this is the one I've been before. This always has to be 1. In fact, this is actually a function, not a value. So it's saying that a counted 0 is a function that you give it no parameters and returns something that has this relationship. It returns a proof and also the 1. So I think I match it. Yeah, right here. So PF4 is the proof, and then N4 is the actual number. Again, even though it's like I don't restate the relationship here. Like I don't say, oh yeah, this is N, so on. But ATS knows it. So once you have the relationship set up, they remain like that. So if I were to go in here, if I were to use N4 and pass it elsewhere, it would still it'd still be connected to counted. Yeah, and I mean, it's not like kind of a change. If I add N4 to 1, I get a new value, it would have no relationship, except it would still know that that's +1. So yeah, it's smart. It's not super smart. There are things like you can't have like if I were to say instead of just +4, if I say it's the power of 2, power of 4, it's like no, I can't do that. Say n times 4, it can actually do that either. Well, it can if you use a different solver, but normally it doesn't. All right. So let's go to slow count. This is a count that counts to a number properly with all it's all proof through. So this is definitely counts. We've successfully implemented counting, and I know we have because it has to construct the counted according to the rules here. So I don't have like a random like counted whatever you want. Yeah, you can't just create a counted whatever and pass it whatever. There are two ways. You have to start at 1, or you have to start from a previous rendition of counted. So you have to start from 1 and go 1 by 1 by 1. It's like n minus 1 and n. So n is always +1. It's always 1 plus whatever you pass it. So you have to count you have to count in order to get to the number just based on the way the data prop is created. So if I start at counted start, I do right here, and I go through a loop and I keep creating counted next that depend on the previous proof. I keep adding numbers. Then I'll end up with a final proof that I return. These are the return types. So loop actually returns the PF here. So this is the final proof, the final number, and it's definitely right. So if I were to change this loop to where it no longer counted properly, if I try to skip numbers, I would fail. You can't skip numbers and still create the proofs. Or if I were to change the property to no longer work, of course it would no longer work. So I've got the logic of counting numbers stated twice. I've got it once, and the loop and how the loop works just goes and adds 1 to. It starts at 1 right here. This is the first I, and then each iteration it adds 1 to it until it gets to n, my target number. And it returns n in this case, but it knows it should probably return I, but either way, ATS knows that these are the same numbers at this point. And I'm just using I like an I in a for loop in some other language. It's just the thing you add, you change to get through the loop. the iterator. No. Anyway, the index to like an array is what that comes from. Anyway, so this is correct. This is definitely correct. It would be very difficult to screw this up or add a bug to it, because I've got the logic of it expressed two ways, in two completely separate ways, and ATS ATS ensures that those ways, those two separate expressions of the logic, match up with each other, and they match up with each other where I've connected them. So again, through like simple numerical assertions. So in this case, it's just a one-to-one equivalence. I'm saying counted in and end in, so it's the same number. They have to be the same. All right. So this does it. This is confirms this is correct. Yeah. And I can go and be even clearer, like, okay, this has to be counted 42. But no compile time errors. That's fine. And then here's fast count. In this case, I'm cheating. So I'm still using the data props and everything, but I happen to know, I know because I've been through elementary school, that in fact, like, all natural numbers are countable. So if you give me a number, no matter how high, I can definitely count to it. Just going one by one. I don't actually have to do that in a program. I just know that that's the case. So what I have here is I have an external proxy that says, okay, somewhere, not here, in fact, not anywhere, I have a function that says that actually, if you give it any kind of natural number, it's going to say that is returning the proof for the counted. So yeah, give me any number. Yeah, here's your proof. It's totally countable. I promise. But I don't actually implement that. I just say that it's there, and then I use prval to assign this proof variable. It's not a real variable that exists at runtime. It's just a proof variable that ATS manages while compiling and doing all its analysis. And I pass this function right here in. So yeah, here's n. Tell me that it's countable. Yeah, it's definitely countable, and then I return that. So from the caller's perspective, this function is exactly the same as this function. You give it a number and it returns a proof for that number, as well as the number itself. And that's the case here, except this one cheats. In fact, it's more efficient. If you look at the actual generated C for this, there's nothing in it. It's just an empty function. There's returns whatever you give it, which probably gets compiled out of existence entirely. So yeah, this fast count is just it's like constantly for or constant for or something. All right, and here's a usage of that. Yeah. So fast count 42, slow count 42. Yeah. So in this case, of course, I could potentially have a bug. So it's like ATS, like, it gives you tools, but it also it doesn't constrain you to those tools. So like there could be a bug, but at least looking at it, like, okay, I'm declaring this is the case. This is always the case. And I even spelled it out in English. So it's like I'm being as clear as possible, even though there could be a bug here. Like I could return like n plus 1. I don't think it'll let me do that. Yeah, you can lie, but not like this. Yeah, now I'm lying. I definitely come to 42. What? Oh, plus 1. It doesn't like it. I said all nats are countable. Oh, but it still knows that it's not the same. So this, even though I try to lie, I'm still saying right here that the counted proof and the int proof have a relationship together. They're the same. So I'd have to break that relationship in order to finish lying. All right, now that'll definitely allow that. But no. Oh, down here, I'm again. All right, let's break it also in the caller display in the caller, since I repeated that. No, it still doesn't like it. It's very difficult to lie. I'm saying it here too. All right, I actually can't do that then. No, this is an assertion. This shouldn't be constraining me. This should be completely fine. Don't use it. Right. Hmm. Now you can't actually lie even about like even though there's a numerical relationship and ATS can see what it is. I should still be able to lie in that case. In fact, let me demonstrate that as a completely separate thing. Okay. I feel like lying, knowing how to lie is important. Like knowing how to break the rules is important because it gives you a better idea of what your actual safeties are. So, like like that's why I emphasize like if you don't have a connection, you can do anything. Like you have to actually set up that relationship in order for this to matter, and you can't just create any kind of random data prop and have it be good. Like I said, if you create a constructor here that accepted arbitrary stuff, that then you can just create a proof for any random number just by creating it, and it wouldn't actually it wouldn't actually force you to go through the process of sort of creating it from previous versions. And this right here is very similar to what Prolog would look like. Like if you're like the proof for a factorial looks like an implementation of factorial in Prolog. So this right here. All right. Anyway, go back. So again, we're talking about lying about numbers. So let's say funnel is 0, takes an int, not just any int. Actually, we don't have to do it like this. We could do it like this and say int and n equals 0. But if it is going to be just a number, a particular number like that, we can do what we did before and say always 0 takes an n, or a number, which is int of 0. That's the 0. Instead of saying this is a variable and the variable is 0, we just put 0 there. All right. And it doesn't return anything. It says print. All right. So disaster calendar. And then we're saying, oh yeah, it's been some number of days since the last disaster. And we're saying right here that number is always 0. So let's make that. I'm going to try and tell it, oh, it's been 5 days. So no, you can't do that. It's making the other one. Make always 0. All right, that's not the lookup problem before. Implement main 0 equals disaster calendar. Yeah. Oh, like that. Yeah. Now it's definitely saying this. Hey, 5, like this int 5 right here, that's not the same thing as 0. 5 is not 0. You got that wrong. You can't do that. So this, I have to pass it 0 for that to be the case. Once again. All right, now it's fine. So 0 days is the last disaster. Now let's say n, where it's 5, and so we're creating an extern praxis, or it's like an axiomatic assertion somewhere out there. I'm not going to tell you where. There's a function that proves that this number you're giving me is actually 0. But, I don't think I have to do it like that. That's all I wanted to do. I was saying 5 isn't 0 on line 7. here. I really should have brushed up on how to lie. Let me. I don't have that right nearby. So I create the lemma. The lemma at 0. Normally assertion like this would start with lemma. It's like this. Yeah, like that. It's been 5 days since the last disaster. So now, disaster calendar here, it says, oh yeah, you have to pass me an int, and the int has to be 0. It has to be refined by 0. And over here, I'm lying. I'm saying, oh yeah, give me whatever. 5, sure. 5 is actually 0. Like it's the int, the type, like the data is still 5. I'm not actually changing the 5. You can see it when it prints out that it's in fact 5. It's been 5 days since the last disaster. But I'm changing what ATS thinks is the refinement of it. So normally a number is always like it's not int. It's always going to be like an int of 5 unless you type it and strip that away. But by default, like a literal 5 is going to be an int of 5. If I add 1 to that, it'll be an int of 6. ATS will keep track of all that. But now I'm saying that 5 right there, it's actually an int of 0. I promise. I swear. I've got this proof. It's a really elaborate proof. It's not implemented anywhere, but it totally tells you that 5 is actually 0. And then I use it and I apply into that. So it says, oh yeah, and it's actually int 0, and then it lets this work, even though over here it says it's totally fine. So the protections that ATS gives you, it's not like Java protections. It's not like it protects you from other programmers in your own team, or I can link an arbitrary code and it'll totally be safe. Like no, it doesn't give you that. Especially since there are no runtime protections. These are all compile time, statically determined stuff. If I link an arbitrary code, it's only going to work if that code really is from the static. Really is what I said it was when I started it was in whatever FFI or such. So yeah, it doesn't protect you from yourself or your other team members. It doesn't protect you from its like deliberate abuse. So you wouldn't use this for like a plugin system that you can't that would allow arbitrary code to run. But what it does do is it lets you do double entry bookkeeping. It lets you it lets you state the logic of your program twice in 2 different ways. And it lets you say there's a relationship between these 2 ways, specific relationships that it checks and maintains, and it tells you when you screw them up. With the one weird extra case that a wizard was allowed. So does it complain about this? I can't actually. I messed up on. I left proof count in a weird state. So this is a jobs. Make jobs. Jobs is fine. No problem with jobs. We got plenty of jobs. And I can't actually exploit this bug. Like I can't pass it a wizard, and I can't ever say if I say like, oh, I can't actually get a mage from it or anything like that. So it's a little bit weird. It's kind of an edge case that we ran into all talking about this. Yeah, this is the basics of like type refinement and dependent types in ATS with a little bit of proofing, very little bit. Like I only talked about this counted, and I probably didn't go into like the depth it needs. But maybe this very simple example will help you out. This is the part of ATS that makes ATS like. This is why you say, okay, well, NIM has, or NIM, or Ocaml or Crystal, they're comparably performant. ATS probably beats them on it. I've seen ATS beat them on its own grounds, even without this. So ATS has other advantages elsewhere, but this is what makes it this is what really makes the language. This is also what makes the language a little bit hard. Like the weird errors you get are invariably constraint errors. If you try to start like a normal program, do something with arrays, and you get a lot of problems immediately. Well, it's because arrays have to have a whole bunch of constraints on them. So the language doesn't just let you index out of bounds or things like that. Your default types, the default library that you load in, includes a lot of dependent types, a lot of properties and stuff like this. So you have a lot of constraints on you by default. And so you run into those, you get weird errors, and like, what's going on? But for that reason, I think it might be useful to create like an alternate standard library that doesn't actually use any dependent types anywhere. In that case, like normal like ATS programming would be very direct and easy, just the same way it is in other languages. Like you wouldn't run into weird errors. It'll just let you do something and let you shoot your foot off, just like you want, right? And then you can tighten the screws on that and add in your own constraints. But then eventually be like, well, let's re-implement the standard library. So I think it'd be useful as like for pedagogical purposes, for learning the language. I think a standard library like that would be useful. But for actually using the language, it's easy just to get used to it and kind of learn this and learn what guarantees the standard library has in it. All right, that's it.